How many of you have heard of Reframe Systems? Okay, got a few. Awesome, that's pretty sweet. We are a building and development construction company. We build climate resilient homes, and we do it in a factory environment, and we do use robots. The DNA of the company is primarily from Amazon Robotics. So myself and my other two co-founders actually delivered and deployed thousands of robots across dozens of fulfillment centers, warehouses. But here we're really applying a lot of those lessons to construction. Today in particular, we're going to talk about kind of our software to do CAD to fab pipelines. So I'm very excited to do that. My name is Felipe Polito. I've done the DARPA Robotics, the humanoid challenge for about 4 years. So I did a lot of motion planning controls back then, long before kind of humanoids were cool. Since then, I've also spent about 6 years at Amazon Robotics. When I started, the drive unit project was going well along, and we had tons of kind of drive units deployed, but we haven't really done much manipulation. So I spent about 6 years kind of growing from a team of 4 to over 300 manipulation workcells that use machine vision to really kind of do all kinds of tasks within Amazon. So with that, so kind of the opportunity came knocking. Reframe Systems kind of came about. We started talking about the thesis. I got really excited, and I just kind of, I couldn't stop. So I jumped over to Reframe, and I've been there since.
Hi, I'm Ethan Keller, and I come from a pretty different background. So this is a drinking water treatment plant in Honduras. So I was working on designing these about 8 years ago, and designing them in CAD from base kind of hydraulic equations. So we had a system where you could input specific flow rates, and then you could spit out a whole fully specified drinking water treatment plant that we then actually built in Honduras. We have about 16 of those. That's called Agua Clara. And that's kind of where I was introduced to trying to script the notion of creating a building from some pretty rough dimensions or hydraulic constraints or design constraints. Like, how do you take CAD and really make it shine? And then I was hired by Onshape, which is a mechanical CAD system. I'm sure a lot of you know about Onshape. It's really popular in robotics. And I worked there for 6 years on the API and Part Studio teams. That was a blast. And then opportunity came knocking as well for Reframe Systems to lead their design automation team. So that's where I got to apply yet again. How do we actually build scripts that quickly allow us to create buildings, create houses? So that's what I've been working on for the last 2 years with Felipe. Excited to share about it.
Awesome. All right, so what's the problem statement? The United States has a 4.5 million home shortage, and I will say that there is a significant labor shortage just across the labor and the construction process. I'll also say that the construction process is done, the way it is done today, it is very, very inefficient. So there's just a lot of added work and frustration that comes with that. And then the last one is because of the regulatory environment, almost every home in different towns and different cities has to be built as a one-off prototype. You cannot mass customize this type of product because you have to meet all the local demands for zoning and a bunch of other rulings that really forces it to be kind of this very broad customization problem. So who here has done or has kind of suffered the pain of a home renovation project? Raise your hand. Okay, there's a few of you for sure. Generally, it is very tough to do construction. Construction is just a hard thing to do in the US. Normally, the projects are very underspecified, so things are getting figured out on the fly. The fragmented industry makes coordination very, very difficult. And then when you do need feedback from the experts, those tend to take days. So generally, runovers of cost and schedule just are common, or just the norm. So with that, what we have done, and this is not novel to all industries, but it is really kind of interesting in the construction industry, is that we've created a very, very strong pixels to parts pipeline. But basically, we start with a very kind of less detailed, well-defined digital twin of that building. So we basically model every nail, every screw, every wire, everything gets modeled to the last second, long before we get to building. So this digitization process basically lets us have that single source of truth, and we kind of figure out all of those details long before manufacturing. Again, none of this is novel, but really, I think where our secret sauce is really shining is that we're writing software to, over time, codify those rule sets. And that's kind of step number 2 over here on the screen, where we're writing software to design CAD. And over time, we get to a world where the design cost goes to 0. So you can get your mass customization, kind of that high mix, without paying the cost of the digital process of like making that actually exist. We see a world where we're using these tools to then actually start applying LLMs and AI to interpret local zoning codes, and get to a world where you can open up a browser, type in an address, and we can get you a fully defined home that is compliant, along with how long it's going to take and how long it's going to cost you. So that's kind of the reframe process. I would say we're well within 1 today. We're kind of starting to toy on 2, but I'm kind of excited to show some of that as we go through this presentation. It all happens here at our first Microfactory in Andover, Mass. This is the physical manifestation of that digital thread. So it's about 18,000 square foot facility. It is highly flexible the way it's set up. It's inspired by both on-site construction, where you can kind of build anything on the fly, but also a lot of lean manufacturing principles. Some of those learned from Amazon. And for our operators, that means no measuring tapes, no flipping through drawings, no last-minute trips to Home Depot. Just add value work for every hour that you're in the job. So it really just makes that flow a lot more efficiently. We are happy to announce that we did put a building on the ground about 3 weeks ago now. So this is in Somerville, Mass. We poured the foundation, and then within a 4-day process, we bought these modules from the factory to site, and we stacked them on site. So the same truck was round robin from our factory to Somerville. We were setting about 8 of them a day. So end to end, in 4 days, we set up the whole house. We went from foundation to like a fully built, basically, system. And then we take, and now we're kind of going through this 4 to 5 week process where we wrap that building up and hand off the keys. These buildings are very energy efficient. So we built to kind of a very high standard. And the fact that we're building it in a factory means that we can get a lot of high tolerance, like kind of stacks as it goes up. So we know that everything is built as it was designed, and it's built a much higher tolerance than if you were doing it on site with chop saws and measuring tapes. These are some pictures of that project. One thing I'll note is that the big crane kind of moving some of the modules down. But you'll note over here on this bottom image that all of your cabinets, appliances, lights, windows, everything has been pre-installed in the factory. So you're doing very little work when you get to that site. And then the last picture was taken yesterday. The building is now almost fully wrapped up, and we've been working internally to kind of set up all the electrical and kind of just finish it up before we can hand off the keys. So we actually built 2 of those buildings. One is on the ground, and one is currently sitting in our yard, and it's going to go on the ground in about 4 weeks. So that's the 2 triple deckers you see on the top. These are small multi-family 3-unit buildings. We kicked off production for 12-unit community in Davins, Mass, which is the picture you see in the middle. So I'm very excited about, because we get to kind of like build the same thing over and over again and get A/B testing. And then we're also building 2 single-family homes that are coming to LA, just right on the corner over here. With the fires, there is obviously a massive shortage. There's about 6,000 homes that need to be built. And we're building this project, shipping it over across the country with the intent to kind of have a flagship, build a demand, and by end of next year, actually build our first Microfactory in LA to actually help with the rebuild. Go for the next one. And let's talk about the Microfactory. So we see a world where, we see a world where we're building one of these factories for every 5 Home Depots in the country. And the factory itself, 50,000 square feet, is about the size of the garden center of a Home Depot. So you kind of get a visual idea of what that looks like. They're relatively low capex, $5 million. They're very fast to deploy, and that's another thing that we were doing at Amazon. We got to a world where we could deploy a new fulfillment center within 100 days, and we're trying to do the same thing here. So we're speccing equipment, we're speccing robots, everything in a way that we can go from basically getting the keys of a new factory to be able to deliver product within that time frame. And what that means is that now we can get to a world where we're signing contracts for new communities, new areas that we're building, then building the factory, and then providing those homes to those that need it. And with that, I will let us kind of focus a little bit more onto the panels, and I'll let Ethan take it from here.
So I will be taking us through the journey of what it is to first design a panel and then get that design to the robotic chop saw in our robotic arm to actually frame it, and then furthermore, all the processes downstream to build the fully developed panel and then integrate it into a module. So just first, a little bit of terminology. This is a module right here, like in its entirety. So this is what the box is that we were pulling up on the cranes. And every single kind of 2D element, so the walls, the floors, the ceiling, those are all panels. So when I'm talking about framing a panel, it could be a ceiling, it could be a wall, it could be a floor as well. So the first thing we built was this tool within Onshape. And so this is a custom feature within Onshape. And you can specify things like the panel type, which is developed by our in-house architects. And you can specify the rough opening for the window, the door, depending on the specific plan. And the stud spacing is all determined by the combination of that and the specifics of the panel type as well. So you can really specify an infinite number of different panels. And the variation is critical because we're trying to address so many different markets, so many different site conditions. So really, if we can build an infinite number of different panels, that unlocks all sorts of markets that more traditional modular has trouble getting into. Okay, and then what we did was we took that kind of panel tool and we also extended this up to kind of a floor plan tool. So the notion here is that we can build up from those simpler automations and really create a whole suite of tools that allows architects to quickly create a fully detailed CAD system, CAD model, that we can use to effectively construct the house without any kind of ambiguity. Our CAD actually includes like pipes and wires. That's more of a manual process at this point in time. But our goal is to just continue eating that pipeline up and up until we have like really baked in tools. Okay, now the next step was to take those assets that are baked in to that CAD model and then actually make them manufacturable. So here is our chop saw on the upper right hand. That is a robotic chop saw. There's a pusher there that pushes the lumber to a predefined length. And then also there's a print head on it. The print head is critical because that lets us annotate the lumber with whatever we want. And since these are kind of the bones of the module itself, if we annotate them with really specific annotations, it can help downstream processes. So the electrician can look at the annotation and be like, okay, that wire is going here, or the plumber can see it and put the right pipe in. And that's critical, because so much time is taken. Yeah. Yeah, so it's not only that. So like here, for instance, is a whole annotation. But we also label how the studs go together. So for instance, 02 is a particular joint annotation as well. And there you go. Like, so there's tons of annotation that we use. And most important part is we also print fiducials so that our robotic system can actually see the studs and work with them.
Yeah, so again, everybody I think is here is looking for the robot. Here it is. This is our first platform. We're really trying to push on a few key things. And as we talked about it, that small multifamily project that we've just showed you had 176 panels. They're all different. So basically, we fundamentally believe that using software to manage that complexity is key to high-mix manufacturing. And this first robotic work cell platform embodies a lot of that ethos. So we've kind of created a operation flexibility through vision systems. That means for us, printing is very cheap. So we print a lot of these fiducials onto the boards. The robot is able to identify the first fiducial, knows which piece of lumber it is, for which panel, for which project. It pulls that recipe straight from Onshape, and then it gets to work. So operationally now, you can feed in a kit at any point into the work cell, and the robot scans that first stud and knows exactly what to do. Second thing is assembly flexibility. So we really wanted to get a single robot to be able to build these large panels. We wanted this work cell to be kind of cheap, and we wanted to be able to have a flexibility to handle the wide variety of panels that you can think of, including like arches, diagonal walls, trusses, all kinds of different shapes over time. So what we came up with is this kind of back panel you see, which is gray. And then we use these things which we print in-house, which are on and off magnets from the welding industry. And the robot is able to pick these up and then place them anywhere within that panel in any orientation, and then activate to lock it in place. And now this thing is locked to about 400 pounds of force, which means that over time, as we develop kind of new capabilities, it kind of just rolls right into production, and you're not even thinking about what hardware changes you need to do. And then the third one is really a scaling flexibility. This whole work cell is about $200,000, 800 square feet. So as we go to a 50,000 square foot facility, we might have 4 or 6 of these systems. I go to a 100,000 square foot facility, I might have 8, 12 of them. But you can continually scale your automation to get your kind of ROI back, and really kind of just keep playing that game with like operation needs. Particularly proud of kind of an end-of-arm tool design. Again, wrist back, these robots are really off the shelf. You can buy them, you can pick the color you want. They're like quite like kind of standard. But from the wrist forward, a lot of the parts in this tool are all built in-house. We do a lot of 3D printing, a lot of like laser cutting. The first 3 versions of this tool were built with no sensors. We actually were doing open loop assembly, and only by getting there and knowing what the unknown unknowns were, we then started to decide, hey, we need to actually close loop on this. We need to do that. We needed to alter it. So same thing. There are modular pieces that do the vacuum, the gripping, the magnet, and we can continually kind of adapt and redeploy them along with the software changes. So we're just iterating very quickly to get kind of to a state where operations is happy with the output, and our carpenters are happy with the things we're producing. So here's a video of it playing. I will note, this system is heavily in production. That small multifamily that I showed you, about 40% of the panels were built with the system. We're doing about 5 panels a day today. In terms of speed, we basically can build a panel as fast as 2 carpenters on our manual framing table. The robot is currently running at about 20% speed. But it is a 1-ton robot with nail guns at the end of it. So we do like to go slow for now, and over time we can kind of crank that up a lot more. And you can kind of see it here, picking up the magnets and then assembling. Here it's scanning the fiducios. But yeah, producing about 5 panels a day today with the intent that we can kind of just continually build on that quality and then just rolling out more and more features over time. One thing that people always ask is like, lumber is a like natural material, it deforms, it bows, it twists, how does he handle that? And if you notice, when we're doing the nailing, we actually re-grasp each one of those pieces of lumber at the end. So even if the lumber is doing something weird in the middle, we know that that joint is as accurate as the robot can get to it. It just tends to be pretty accurate. So it's a good place to be.
So to continue our journey of making this panel, the next step is to apply this other custom tool that we wrote. Like now that you understand how the robot works, when we apply this tool, this actually generates those instructions that then go straight to the robot, are interpreted by the stack, and translates these movements into the correct movements for the robot itself. You'll notice that we're not doing like any kind of actually trajectory planning here, like within the CAD system. Instead, this is just the layer to get those instructions to the robot. But what it does let us do is visualize how the panel is going to be built. So that's the panel jig that you see in the background. And then those are the magnets, the collision bodies for the magnets. And that's the collision bodies for each of the end-of-arm tools that Felipe just talked about. So what's really nifty about driving the robot instructions directly from CAD is this allows the architects who are used to working within CAD actually understand, are the things that they're trying to build actually robot buildable? So we get that direct information coming back from the robot team back up to the design team. And that's super critical because, like we mentioned earlier, the industry right now is extremely fragmented. So you've probably heard before where architects specify something that can't actually be built because, I don't know, some plumbing gets in the way of HVAC, gets in the way of electrical. That can't really happen with our system because those collisions are discovered at the design phase with this highly detailed CAD model. Okay, then I also wanted to give Foxglove a bit of a shout out here, because when we actually get to production, we do use Foxglove to record events. If anything wrong happens, we can go back in time with Foxglove, download that ROS bag, see exactly what the state was. On the upper right, you can see that's actually an image that is taken with our depth camera of the lumber itself, and then imposed on that. It's a little hard to see, but are actually the detections for each of the fiducials. So it's just a really cool unified system for us to, what is it? Foxglove unlocks continuous development without production compromise. So that's what we've got, and we're really happy with it. So just to summarize, first step is to design this super detailed frame, apply the robot cam, apply the saw cam, then actually cut the lumber, and then frame it on the robot and enjoy a seamless experience. So here we go. There's so much more to building a house than just framing panels. In fact, it's a pretty small part of it. So we have this whole additional software stack, which is for driving those additional operations, which right now are entirely manual. So they're part of our augmented workcells. Here's some examples of how we try to improve the efficiency of those workcells themselves. So for instance, we have some drawing, some IoT stuff going on right there, where you can see a bin is specified with a light so that the technician knows exactly which fitting to pull. We can draw on the sheets. So we can do all of these like little tricks to make people faster, to make them more accurate, to make sure that these typical problems which you hear about, which probably plagued your renovation project, just won't happen in the factory. So we really look at it as an end-to-end problem to optimize.
Awesome. Yeah, that wraps up our talk. I know everybody's probably quite hungry at this point. I do want to thank Foxglove. I want to thank Eclipse for kind of believing in us from day one. It's been really awesome to have them as a partner. And I will say, if this kind of mission speaks to your heart, come talk to us. We're hiring across the board. Thank you.